In section 7.3, we're going to learn how to use the square root property to solve quadratic equations. And basically that says that if x squared equals k, then x will equal plus or minus the square root of k. So notice that there's two solutions, a positive square root of k and a negative square root of k, which we usually just combine together with a plus or a minus sign. So for a simple example of this, let's say we had the equation x squared equals 25. Then the solutions to that would be x equals the positive or the negative square root of 25. Now the square root of 25 is just 5, so x equals positive or negative 5. So there's really two solutions, x equals 5 and x equals negative 5, but we just combine them together by putting a plus or a minus in front of it. And that makes sense because if you square 5, you'll get 25. But also if you square the number negative 5, since a negative times another negative is a positive, that also comes out to be 25. So both of them are valid solutions. Now sometimes when we solve equations this way, we're going to have to simplify certain square roots. And so I want to show you how to do this. We're basically going to be using a property of square roots that the square root of a times b equals the square root of a times the square root of b. And sometimes we can simplify square roots using this property. For example, let's say we had the square root of 12. Now what we want to ask ourselves is there any perfect square that divides into 12? Now a perfect square is a number like 1 or 4 or 9 or 16 or 25. So when you square a number, it's the answer you get. And if there is a perfect square that divides into the number 12, then this can be simplified. Now if there's not a perfect square that divides into it, then it can't be. But in this case, 4 does divide into 12 evenly. So let's break up 12 into 4 times 3. Where 4, I'm going to circle that, is the perfect square because it's 2 times 2. And then once we do that, we can use this property that I just wrote down to break this up into the square root of 4 times the square root of 3. Now remember 4 is the perfect square, so when you take the square root of a 4, you should get a whole number. In this case it's just 2. So the answer would be 2 times the square root of 3. And that's considered to be the simpler form of the square root of 12. So you're trying to make the number under the square root as small as possible. Let's just try another example of that. Let's say we had the square root of 50. Now again, your question is, does any perfect square divide evenly into 50? And in this case, the number 25 divides into it 2 times. So 25 is a perfect square. So if we break that up into the square root of 25 times the square root of 2, remember 25 is a perfect square, so when we take the square root of 25, we just get a whole number, 5. So that's 5 times the square root of 2. Now if there's no perfect square that divides into the original number, then it can't be simplified, and we'll just leave it like it is. Now another thing that we like to do to try to simplify expressions is to rationalize the denominator. And that means to get rid of the square root from the denominator of a fraction. And the way we'll do that, like in this example, we have 5 over the square root of 2. So we'll multiply both the top and the bottom of this fraction by that square root of 2. And of course we multiply fractions straight across. So we do 5 times square root of 2, and that would just be 5 root 2. There's really nothing you can do with that. And then you have the square root of 2 times the square root of 2. And that would just be 2, because when you multiply two identical square roots together, you just get the number that's underneath the square root as your answer. And that's considered to be a simpler form because there's no square root in the denominator. Now let's say we had the square root of 11 over 20. Well, the first thing you'd want to do is break that up into the square root of 11 over the square root of 20. And there's a property that says the square root of a fraction equals the square root of the numerator divided by the square root of the denominator. And then we'd probably want to try to simplify square root of 20. So with square root of 20, 20 breaks into a 4 times a 5. So that's really the square root of 4 times the square root of 5. And remember, the 4 is the perfect square here. And the square root of 4 comes out to just be 2. So it's 2 square root of 5. So when we simplify that down, now we have square root of 11 over 2 times the square root of 5. And we'll multiply both the top and the bottom now by that square root of 5. Now in the numerator, we have the square root of 11 times the square root of 5, and that would be the square root of 55. You can multiply those two insides together since they're both under the square root. And in the denominator, you kind of want to think of doing the square root of 5 times the other square root of 5 first, which would just give you 5, and then multiply that answer by the 2 at the beginning. So it's 5 times 2, which would be 10. And that'd be your simplified answer. Okay, now let's get back to solving the equations that really is the main point of this section, where we have x squared equals some number. So I have two examples here. Let's start with x squared equals 24. Now, according to our property, if x squared equals 24, then x would equal the positive or the negative square root of 24. Now, the only thing we want to do with this is try to simplify the square root of 24 if possible. Now, 4 does divide evenly into 24, and 4 is a perfect square. So we could say x equals the positive or negative square root of 4 times 6, where 4 is a perfect square. So when we break that up, we'll have plus or minus the square root of 4 times the square root of 6. And again, the square root of 4 should come out to be a whole number, and it does. It's just 2. So the answer here would be x equals plus or minus 2 times the square root of 6. And that'd be your simplified answer. Now in this other example, the first step would be to get the p squared to be alone. All right, so this p squared needs to be all by itself on the left side of the equation. So first you'd add 11 to both sides. So 3p squared would equal 14. And then divide both sides by 3. So p squared equals 14 over 3. And then at this point you can say p would be the positive or negative square root of 14 thirds. Now since we have a square root of a fraction, we don't want to leave it that way. We'll use the technique I showed you a minute ago about rationalizing the denominator. And the first step would be to break that up into the square root of 14 divided by the square root of 3. And then at that point, we could multiply both the numerator and the denominator by the square root of 3, the one that's in the bottom. And when we actually do that multiplication, we multiply straight across in each case. So we're going to get the square root of 14 times 3 comes out to be 42. So the square root of 42. And the square root of 3 times another square root of 3 is just 3. And so that would be our simplified answer in this case. Now sometimes instead of just having x squared equals a number, we have some expression inside parentheses squared equals a number. And we can solve this in a similar way. We can say that the expression inside the parentheses, which is x minus 9, would be equal to the positive or negative square root of that number. So it's the same idea, except instead of just having an x, we have x minus 9. So we'd finish this the same way. First try to simplify the square root. Now 25 does divide into 75, so we can simplify that. So that would be plus or minus the square root of 25 times 3. And the square root of 25 is 5, so it would be plus or minus 5 root 3. So right now what we have is x minus 9 equals a plus or a minus 5 times the square root of 3. And we're trying to get x alone to solve for x, so we need to add 9 to both sides. And you could put the plus 9 at the end, but usually people like to write it first before the plus or the minus. So we get x equals 9 plus or minus 5 root 3. And those would be your solutions. Now remember, there's two solutions. One is 9 plus 5 root 3, and the other is 9 minus 5 root 3. Both of them are going to be decimals if you put them into your calculator. Okay, let's try another similar problem, except this one's a little messier. It has some fractions in it. So again, we have some expression inside parentheses squared equals a number. So the expression inside the parentheses, x plus 5/6, will equal plus or minus the square root of that number. Now, the first thing we'd want to do is try to simplify that square root. So let's take the square root of the top and put it over the square root of the bottom. Now the square root of 36 is just 6. Okay, so I can just simplify that. So the equation I have now is x plus 5/6 equals plus or minus the square root of 51 over 6. And I'm trying to solve for x, so I have to subtract 5/6 from both sides. So x equals, and I'll write the negative 5/6 first, and then it's going to be plus or minus the square root of 51 over 6. And since the denominators are common and you're adding or subtracting the fractions, you could put that together into one fraction and say negative 5 plus or minus the square root of 51 all over 6 if you wanted to. Okay, this answer here would also be correct as well. So there's a couple of different ways of writing it. Okay, in this next example, it's a little more complicated. The expression inside parentheses x plus a is squared, but you have some other things attached to it, like the negative 7 is multiplied and the plus 4 are added. So the first step is to get the x plus 8 squared, that part right here, I'll circle it, to be alone. So you'd first subtract 4 from both sides, which would give you a negative 5 on the right-hand side. And then, once you've done that, you would divide both sides by the negative 7 to get rid of that negative 7. So you end up with x plus 8 squared equals, and a negative divided by another negative is positive, so it'd just be 5/7. Once you put it into that form, now you can do it the same as before. You can take the expression inside, x plus 8, and set it equal to positive or negative the square root of the number on the right side. And again, we'd want to try to rationalize that denominator. So x plus 8 equals positive or negative square root of 5 over the square root of 7. And then we can multiply the top and the bottom by square root of 7. So we end up with x plus 8 equals plus or minus the square root of 35, because you can multiply the 5 and the 7 together, over 7. And then just subtract 8 from both sides. So x would be negative 8 plus or minus the square root of 35 over 7. And those would be your solutions. Now sometimes when we solve equations like this, we end up by taking the square root of a negative number. And that's actually an imaginary number. So we have to talk a little bit about imaginary numbers. Now first of all, the basic imaginary unit is the square root of negative 1, which we're going to call I. So the symbol I represents the square root of negative 1. Now that's not a real number because there's no number you can square to get an answer of negative 1. But still, I represents that number, and we're going to call that an imaginary number. And that's the basic imaginary number. And if we have the square root of any negative number, like let's say it's the square root of negative 25, that's an imaginary number. So anytime you have a square root of a negative number, it would be an imaginary number. And we want to kind of think of that as being the square root of 25 times the square root of negative 1. So it would be 5i. So we want to be able to represent the square root of a negative number in terms of I. Here's another example. Let's say we had negative the square root of negative 45. Well, the square root of negative 45 right there is an imaginary number. And it's also negative because there's a negative sign in front of it. But we want to simplify that imaginary part down first. So we'll do negative. Think of 45 as being 9 times 5. And then times negative 1 because it's negative 45. And if you break that up into 3 separate square roots, you have the square root of 9, and then the square root of 5, and then the square root of negative 1. And the square root of 9 is just 3, and the square root of negative 1 is I, and the square root of 5, there's nothing we can do with it. So the answer for that would be negative 3 root 5 times I. Now numbers like these are called imaginary numbers because they're in the form b times I. So when you have a number b times I, that's called an imaginary number. Like in this first example, b is 5, so that's b times I, where b is 5. In this next example, b is the number negative 3 root 5, so it's still b times I. Sometimes we'll run into other kinds of numbers where we have something that's in the form a plus bi, where a and b can be any real numbers. And that kind of number is called a complex number. And that's important because we're going to be working more with those in the next couple sections. So anything of the form a plus bi, where a and b can be any numbers at all, is called a complex number. Now let's say we wanted to solve the equation x squared equals negative 32. Well, by our property, x should equal the positive or the negative square root of the number negative 32. But you see, since we're taking the square root of a negative number, that will be an imaginary solution. We'll still try to simplify it. Square root of 32 breaks down into, it would be a 16 times a 2 times a negative 1, where the square root of 16 would be 4, and the square root of negative 1 would be I. So the solution would be plus or minus 4 root 2 times I. And notice you're getting imaginary solutions now. Now let's try the equation x minus 2 quantity squared equals negative 81. So to solve this, the expression inside the parentheses, x minus 2, should equal the positive or negative square root of negative 81. Now, the square root of negative 81 is an imaginary number because, again, it's the square root of a negative number. And that would actually be 9i. So we have here x minus 2 equals plus or minus 9i. And then we'll add 2 to both sides to solve for the x. And again, we'll write that 2 in before the plus or the minus sign. So it'll be 2 plus or minus 9i. And notice the solutions here are actually complex numbers. They're of the form a plus bi, where a is 2 and b is either 9 or negative 9, depending on which you use, whether you use the plus or the minus. So there's complex solutions here. And these solutions here are imaginary solutions because there's just a bi. Let's say we had the equation t plus 8 quantity squared equals negative 40. So we'd say that t plus 8 would equal the positive or the negative square root of negative 40. Now again, square root of negative 40, that's an imaginary number. And you'd want to break that down and try to simplify it and write it in terms of I. And the way to think of that is it's going to be the square root of 4 is a perfect square times 10 times negative 1. And when you split that into 3 parts, it's square root of 4, square root of 10, and square root of negative 1, which would be 2 root 10, you can't do anything with, and then I. So what we have is t plus 8 equals plus or minus 2 root 10 I. And then to finish it, you just subtract 8 from both sides. So t equals negative 8 plus or minus 2 root 10 I. And those are also complex solutions because they're of the form a, which would be negative 8, plus bi, where b is 2 root 10 or negative 2 root 10. Now this method for solving equations can be used to make predictions when you're working with a model that's in vertex form. Like in this example, the function that's given here models the annual revenue of Goldman Sachs in billions of dollars t years after 2000. So let's say we want to predict the years when the revenue was $52 billion. So this number 52, we'd want to substitute it in on the left side of the equation. So we'd end up with the equation 52 equals 2.3 times t minus 2.72 squared plus 9.87. Now to solve this, first of all, we have to get this expression, this squared expression that's inside the parentheses, to be alone on one side of the equation. So first you would subtract 9.87 from both sides of the equation. And that comes out to be 42.13 equals 2.3 times t minus 2.72 squared. And then you divide both sides by the 2.3. So 42.13 divided by 2.3 comes out to be 18, I'm going to round it a little, 0.32. And now, since we've got the squared set of parentheses by itself, we can take the positive and the negative square root. So we would say, I'm going to flip the sides of the equation, so that t minus 2.72 would equal the positive or negative square root of 18.32. Now in an application like this, you'd like to just convert the square root of 18.32 to a decimal. And when I put that in my calculator, it comes out to be about 4.28. So we have t minus 2.72 equals plus or minus 4.28. And then we'll add the 2.72 to both sides of our equation, which gives us t equals 2.72 plus or minus 4.28. So there's two solutions here. If you use the minus sign, you'd have 2.72 minus 4.28. That comes out to be negative 1.56. And if you use the plus sign and you add it, you get 7. So since these are measured in time from year 2000, this really means, this first solution means 1.56 years before the year 2000, and this second solution means 7 years after the year 2000. So we could say it would happen in the years 1998, that's 2 years before 2000, and 2007, 7 years after the year 2000.